First of all, it is amazing to be part of Data Platform Summit. Knowing there are more than 9,000 registrations itself is a little overwhelming. I'm glad I had an opportunity to present in such a wonderful forum that way. Okay, so I'll give my best to see how I can help understand or make people aware of some of the new concepts that we have developed at Kindred. Okay, so before I get started, we started this week, at least here in India, on a Teacher's Day. 5th of September, we celebrate as the Teacher's Day. So I thought, while I'm trying to do a little bit of teaching, why don't I remember my teacher as well? A small little quote that my advisor mentioned is what I want to share with you all. If we ask any kind of a question, say just energy, what is energy, or what is a plant, what is flower, etc., anything like this, right? So if we ask this to a bachelor studying student, either an engineering student or any bachelor student, then the kind of answer we get is very clear, crisp, very neat, just like in the textbook. The same question, on the other hand, if we ask to a master studying student, then we can kind of get an answer. Okay, so he will give some answer, so it's kind of like an answer. Okay, but the same question when asked to a PhD student, we should be happy if we can get some kind of an answer. Higher education is getting confused at a much higher degree. Okay.
Sorry for the interruption, Dr. Sheela. So your Teams messages are popping up on the screen. So just to notify you, you can just close that window completely. Exit Teams so that the pop-up will not come. Yeah.
Okay. So hope that helps. Okay.
Yeah. Thank you.
Thanks. Okay, so thereby today I don't intend to give a very higher education or anything, but for somebody who is very new to computer vision and image processing related activities, it will be a very nice journey. For somebody who is kind of aware of at least the basics and how to go about, it's going to be a wonderful education. So that's what I want to do in today's session. Okay, with this, let me get started to the actual theme, what I'm here for today. So if you see all these pictures, okay, and if the idea is to know where there is water, okay, then the very common approach, very well-known approach, is to start going ahead and start annotating it. So first we have to mark where there is water. Okay, so for example, in this picture, we can say this is the place where there is water. Similarly, in this picture, we can say where there is water. In case there is no water, in just like in the other two cases, there is no annotation done. Okay, so kind of the way in object detection or supervised learning, so where we have to teach the computer or we have to teach the algorithm that whenever you say something like this is called as water. So whenever we put some scenic pictures, and if we need to know if there is any kind of water, we will get to know, and it could be in this particular format. Okay, and this goes on. So if there is no annotation, then there is nothing in place over there. Similarly, if you take any other, so what is very common is in terms of animals or in terms of cars, which we have very well noticed, right? So here there is car, and we literally mark this out. Imagine the effort that goes out in marking these. Okay, so there is plenty of things. First of all, there is a human needed to kind of first identify himself whether there is the object of interest present or not. And then once it is, then we have to literally mark. I mean, it cannot be, very, a superimposed one with more areas covered and things like that. So it has to be a very neat, just carving out exactly where there is the object of interest. It is a lot of time consumption. It's a lot of effort for that matter. And this is the way it's going on today. Okay, typically a supervised approach. if you take any kind of an industry, okay, so whether it is a fabric, for example, the first picture that you see on the top, you see that there's a fabric and there is a defect in the fabric manufacturing. Okay, so say there is tear or a hole kind of a thing, then we need to identify those. So in order to identify those, again, there needs to be a marking around that area. If it is any kind of an healthcare image, right? So if there is any abnormality in the X-rays or in any scanning related things, then again those have to be marked. In case of a metal sheet and so on. So all these. So basically what I'm trying to put across is, if it's different domain, then there is a need of a skill to itself identify what is called as an anomaly. Okay. Sometimes on the roads, also they say on the road, if there is any kind of a sharp object, pin, nails, or anything of that sort, then there needs to be an alert coming in. So anomalies come in place in many sectors that we see in our day-to-day life, and there is a need to identify those. So thereby, keep on marking one by one. So here, for example, this is an extra run that you see, and there is an extra metal coming in place. So like this, it goes on. Okay, it goes on and on and on, and it's a never stopping journey. But in today's world, if we keep doing this, practically speaking, there could be infinite number of different kinds of varieties of these kind of anomalies, if you take it in a holistic note. So are we still going to sit and mark? Is our future going to still look so tedious and so difficult, or so, I should say, not so challenging, or is it going to still remain that boring? We do not want that scenario. Okay, so thereby, let me take an example of. So these are just some markings to say, how we go about. But I'm just taking you through manufacturing exercise or a domain for that matter, to help you understand how we are trying to overcome this tedious process which is there existing today. Okay. So you might have seen some amazing equipment, CNC machines, and many parts getting done. Very complex parts, very simple parts. All of this, at a fraction of a second, you can see the item starts moving around. Okay. So in this area, now if we, I'm just taking the data here. So the data here on the left side, what you see is just some metal sheet. So if we take a very simple, plain vanilla metal sheet manufacturing that goes on, we know what is on the left-hand side is something very normal image. Normal in the sense there is absolutely no anomalies or no defects identified over there. In fact, even in this case, the picture here that you see is a defect-free item. But on the other hand, whatever you see on these other pictures here are all having one or the other kind of a defect. Okay, so if we go by the traditional approach, the idea is again to mark out all of this. Okay, now again, in some of the cases you can see it's not just a type of the kind of an anomaly is not just something that you can count on your finger tips. Okay, there are so many, it could be in hundreds at times, though the variety could be as many as them, but the heavy part of it, or most of the defects would be type of defects would lie within the top 5 or something of that sort. Okay, and so I'm just giving you a simple example of how things go on here. Okay, now this is the conveyor belt, and the part is moving. Okay, so the idea is to mount the camera at a certain angle, certain position, one or more cameras, to take pictures at different angles of the particular product. Okay, and the moment you take the image, so what happens is there is a person who is doing the annotation. That means there is a hard copy of the image, or sometimes even the soft copy of the image, which they take, and this person has to keep marking. You will not believe, depending on, say, if you're looking around 5 to 6 different types of defects, then at least for each type of a defect, if you want around 200, 300 different data samples, that's a bare minimal. Okay, so you really need more than that. The more, the better, of course. Okay, So we expect them to wait for days together, carve out all of this and give it to us. This is typically done by the subject matter expert who actually trains in terms of, what is an anomaly and what is not an anomaly. Now, this is going to take its own time and own effort by this person here to do the annotation. After the annotation, the data is now going to the algorithm, or there is a data scientist here trying to understand between defective and non-defective and trying to classify whether the item is a good item or a bad item. Okay, if it's a good item, then on the go it will say, okay, it's a good part, so it keeps moving. If it's on the other hand a defective piece, then it comes to another bin. Okay, so once it comes to another bin, then what happens? Then again there is this person from the domain, that means a person in the manufacturing plant, who will then again start looking at the defective pieces one by one to see what type of a defect it is, how big the defect it is, and accordingly see whether it has to be recycled simply because it's too horrible and you just can't fix it. On the other hand, if it's fixable, then they'll just go ahead and fix it. Okay, so he tries to again classify them into two different baskets. So most of the solutions today are in a position to do this, and you don't really need here a data scientist because the algorithm is already sitting on the cloud or on the edge, or sometimes on-prem server as well. Okay. Now, but there is a amazing algorithm which the data scientists would have coded, and then it is made available here. Are we repeating the same thing? Certainly not. So what is the difference that we would want to bring in when we are developing this solution? Okay. So we saw this part where there is amazing part going there, but what we want to do is we want to get rid of this entire effort where there is this subject matter expert sitting there and doing the annotation. We also want to get rid of the data scientist involvement for every single type of a part. That means if the part is a metal sheet versus a pipe versus another curvy structure, or different parts that are getting manufactured, right? A leather sheet or a fabric for that matter. So depending on even though there is a change in the product, we do not want an interference every time from a data scientist to come in and develop an algorithm for each one of them. Okay. So, or in other words, we have an algorithm which can adapt itself to a given situation or a circumstance and kind of automate itself to be able to take care of the changes that are there. And one more is, so once it is defective, we do not want to give the entire effort again back to the manufacturing plant to say, you do the next step, whatever you want to do. What we are planning to do is, or what we have already done is, if the magnitude of the defect is big enough, then, and depending on the type of the defect, we'll just go ahead and scrap it. Or if it's small, the magnitude is small, then we go ahead and say it's a defect type 1 or a defect type 2, depending on what type of a defect it is. Or in other words, we say that if the defect is a crack, then it goes to first bin. If it's a hole or a dent, it goes to second bin. If it's some other variety, if it's a complete crack, then it goes to a third bin, and so on and so forth. Okay, which means the algorithm that we have developed not only says the part is good or bad, it also goes one level forward to say what type of a defect it is. It says what is the magnitude of the defect, and practically replacing this person's job here. Okay. Let me correct myself, maybe not replacing, but most of the job that is done by this individual is kind of automated and done by us. If there is a need to manually check once again, that's fine either. Okay, that's fine as well. Now, once these parts are here, so you might have a question. Okay, so you're more or less getting rid of 3 different main activities, and you're kind of having a very generic model. How are you doing this? And that's the crux of our work. So first, let me go to this person where we are trying to do this annotation completely through ourselves. How are we doing it? Doesn't mean we are going to do that manually. Okay, so what I mean here is that we will get the support of data science, or we are developing a data science algorithm which will do the annotation for us. Okay, and it is, as I was saying, it is not that if it's only a metal sheet we will do this. We could have this done for any given part type. Okay. How are we doing this? I'll give you the logic behind. So let's say there are a bunch of images that come in, which are both good and bad. Okay. So there is a bunch that comes to you and it gets thrown in front of you. Now, very simply, now the first task at hand is, how do I first say this is a good one versus a bad one? There are a bunch of unsupervised approaches or learning methods that are there. In spite of that, there is some hesitation to consume some of the unsupervised approaches. But the kind of logic that we are using here is very simple. So what we do is we take these parts, we try to cluster them. Okay, so to begin with, we just want to have two different clusters. And we want to see whether the clustering approach is able to take the defective versus the non-defective as a feature for clustering, and thereby differentiate between the two clusters. Depending on the part, it is possible that you have amazing results that it will literally classify two differently, but it need not be the case as well. Okay, I am with you. So if the two clusters are somewhat, far apart like this, then it's amazing. I mean, you have taken the very easy or the best part, or, you are in the wonderful zone. So it's good for you. You can literally use this for your first level classification to say that, I know what is good and what is bad. Automatically, the classification has taken place. So now I will use this for my next step. On the other hand, if the data happens to lie somewhat like this, okay, so where you see there is some region where there is an infringement of both the green color and the blue color. Okay, now what do we do? Is the question. So kind of there is the zone or a region which I'm highlighting here, a region where you're kind of lost to say whether do you want to bucket this under the good one or the bad one, which is a little confusing, or it's not clear. Okay, in such a scenario, what we want to do is we want to actually create three different clusters. One is, I know for sure this is the good region, or all these points are good parts. And there is another one which is to say that, these are all bad parts. And the region which is kind of, not clear, it's kind of confusing, then we call this as I don't know cluster. Okay, literally, I don't know whether it's a good part or a bad part. So simple put, it's an I don't know cluster. Okay, it's fair enough to have this. So instead of a two-way clustering, we go with a three-way. And the idea is to kind of discard these points out of our analysis. And so all that would happen is you will lose out some points, but you're not losing out anything beyond that. Okay, so it's okay to lose those points, and all you are going to get is this two well-defined clusters which are far apart, to be able to explicitly, or in 100% of the times, that this is a good cluster and this is a bad parts cluster. Okay, great. Now, this is what we are here assuming. So the bigger the cluster size, or in other words, even the cluster size is small, that doesn't matter. But if the number, based on the sample size points, if the numbers of the sample size is really big, then we know it's a good part. The reason why we want to make this assumption is typically we have noticed that the percentage of defective parts are way less than the percentage of products that are produced in good way, okay, or good parts. So typically not more than 20% in any case we have seen are bad parts produced. So typically sometimes 10%, 12%, or even 1% is also what we have noticed. So thereby the fundamental assumption here is that the cluster which has maximum sample size is the cluster which has the good parts, and the cluster which has the smaller sample size is the cluster which is the bad parts. Okay. Now, since we are taking only the area or the zones which are core to say for 100% sure that this is a good versus this is a bad. So any point that falls within this zone, for sure what it is. Okay. Fine. So for the time being, just leave aside the fact that what's coming in the space outside or things like that. Good. So first step is now clear. Now we go to the next step. Next step is we take only that small sample size cluster which has only defective parts images in that. Okay. And now we do the same exercise of clustering it. You could use any approach to cluster, so there is no specific way. You could get as simple as even just taking k-means cluster or anything. Nothing specific to which clustering approach you need to be following. Just allow it to cluster. So even if you take 4, 5, so use the knee curve model to find out what is the right number of clusters that you need to arrive at, and accordingly you can just go ahead and have the number of clusters defined. Okay. In our exercise, we started with the total sample of images that we received to be around 12,000 images, of which once it became the defective pieces were only 3,000 images. And from the 3,000, we just went ahead to kind of classify 4 different types of defects. And the good news is that it was able to bring out the 4 different types of clusters based on the defect type. Okay. Now, in first go itself, did we get up to 90%? For different types of data, so we did take some were metal sheet, plain metal sheets, some were a little complex designs that we also considered to find out whether it's able to capture the defective pieces. So anywhere between 80 to 90% is a very decently you can expect the classification to or the clustering to take place. Now, just because it is doing around 80% or even 70%, to be very, very pessimistic note, okay? Even if it does the clustering to that level, is it good enough? Okay, can I take it as is? Well, not really. You cannot use it as is. So what is the next step that we do here is say we the number of clusters k is equal to 3 is what it comes. So 3 different types of defects were there. And if you notice that the clusters were more or less in this format, defect type 1, 2, and 3 were kind of overlaying one on top of the other in this format, then you cannot consume the same cluster information to go ahead and classify your parts in the real life scenario, because you will have a lot more false negatives and false positives for that matter. So thereby, what we want to do, or what we have done in this case, is we go ahead and remove the outer part of it, or in other words, something which is kind of core to the cluster is what we retain. Okay, so very dense area within for a cluster is what we retain, and kind of getting rid of the outer layer or outer superficial layer where typically the density is low. So we grab hold of the core part of it. Now, in the process of doing this, of course, again, we are losing out data. Never mind, we'll still keep continuing to do this. So you can do 1 iteration, 2 iterations, or 3 iterations until and unless you feel that, I have completely kind of taken out and I'm in a position to define cluster 1 versus 2 versus 3. Okay, so you can see the difference between the first initial cluster that we received versus after the second round of iteration that we do in the clustering. So we kind of have got rid of all these, and you can clearly see in the black cluster that, it's kind of quote unquote independent of the other 2 cases. Okay, so this is how you will end up getting the very core part of the cluster, which precisely has images only pertaining to those types of defects. Or in other words, the possibility of misclassification is very, very low when you start picking up the core or the very dense area within that cluster. Okay. You might say, okay, if we lose out so much of information, then what's the fun? So, but at least what you know, the way of looking at this is what if we had received a very small sample size of data in the first go itself. Okay. So anyway, so finally we have landed up with, say, in our case, we had 4 different types of clusters. And now with all the cleaning or identifying the dense regions, etc. So this is just a theoretical representation here for your understanding purpose, that we have 4 different clusters. And this, of course, is a very small cluster in terms of the sample size. Okay. And that's the only concern here, that though you are now able to identify all of these, one, you have all the defect that the sample size is very minimal. One of the very common solutions when the sample size is minimal is so of course I do understand you're feeling sad about the fact that you have a very small sample size, but there is always a solution to it, that you could go ahead and do the data augmentation. So you could rotate the images, you could tilt it by 90 degrees, 180 degrees, you could change the brightness, you could crop some part of the images, so many things, whatever works better to make sure you have got a decent size of a sample, so that there is a possibility of the algorithm to consume this as a valid sample size to be able to learn the concepts of that particular type of a defect. Okay, so now, so data is ready. So first is we have good parts versus bad parts. And for the ones which are bad, we also know what type of a defect they are. So this is how we have the data ready with us at this time, or annotated images bucketed accordingly. Next is when it comes to real time, how does it work? Okay, so on a real time, so there is a part coming in from the top. So the first bit is using this cluster, that's the good versus the bad kind of a cluster. You have now developed an algorithm, which is a supervised learning algorithm. Okay, so the data annotation is ready. So you use any simple classification algorithm that you feel okay with, so that's not so much of a thing. Only marginal differences in terms of accuracy, that's the only thing that you can see as a difference versus one versus the other, and so on. Okay, so you pick any kind of a classification algorithm, you would have trained this saying this is what is a good, this versus a bad, and if the part comes in and then it goes to a defective class here, then you will have to next run the second algorithm, which is based on these 4 defect class types. Okay, so you have 4 classes here. Again, you will run the classification algorithm on with these 4 different classes, and then you will take this part, move it into this kind of a classification algorithm to find out which type of a defect it falls under. Okay, so it could fall under type 1, type 2, or any of these. Okay, so good. So now you have kind of completed from one part to a second stage to a third stage. Okay, so our journey did not stop here. So we went on forward to say that annotation is over. Now we have also developed a supervised classification algorithm to learn each one of these. Okay, what next? Yes, you're all happy. I do understand. At least one stage is over. Okay, we now move on to the next stage where we wanted to know the magnitude of the defect. Okay, see why the algorithm so far is only able to classify a given part as defective and defective type 1, it is not locating where the defect is. Okay? And it is not telling how big the defect is. So what we wanted to do next. And in order to find that, so here is a sample image we took, and then we wanted to know how to get the magnitude. Okay. We went on with edge detection methods. So you just take an edge detection algorithm and it will actually help you carve the contours out, and you can actually get the bounding box around that. Okay, so if you take it's the bounding box is not so crisp and neat to begin with. It will draw contours around it, and if you wish to, you can convert that contour into a superset bounding box also. Okay, so let's assume this is the contour that it gave. Okay, now, but when we started doing this for many of the images that we had, then we started getting contours like this. That means practically we had expected only one contour for a given image. Okay, that is because our assumption or what we thought was on a given metal sheet or on a given image of this part, only one type of an image will be there. That is what our supervised algorithms are also trying to do. It will, even if there are more than one place where there is a defect, it will just go ahead and classify into any one of those. It will not say this is having 3 different types of defects in it. Okay, so it's not doing that multi-defect. At least the very well established ones. Though in literature and academia, we do see quite a few solutions which are able to address multiple defects as well. So what we realized in our journey is in some of the images, it started drawing many such contours like this. And to our surprise, we observed that, some of the contours were giving one type of, manually when we observe this, so you can notice that, the type of defect here is versus to another contour is a different type of a defect. Then we kind of changed our minds and we decided, when we actually pulled all of these, when we cropped the contours out and we saw this is what we noticed, and we then said, okay, instead of going for magnitude of the defect, it's time for us to actually do the multi-defect identification. So because this was just one amazing insight that we got during the process of learning. Okay, so we knew we could go ahead and do multi-defect identification. But how do we do this? What do we do after this was also a question. Okay, just like when we extracted each one of this and we started analyzing, and there are multiple types of defects. Sometimes it could be the same type. Sometimes it could be a combination or like 1 or 2. Sometimes it could be more than 2. In practical scenario also, we have noticed this. So say there is a drilling activity going on. They make a drill and there is a hole. Adjacent to it, there is a possibility of a crack. Okay, and the drill size, also the drill hole that they make also could not be done correctly. So there could be a defect in that area as well. So 2 different types of defects in the same image in the same part, for that matter, is possible. So we wanted to get it more reality, and what we decided was to identify the type of these defects. For any given image, if there is more than one contour, we crop that part, pull that aside, and now this becomes independent image. Okay, so we crop all the contours where we find these anomalies or where we find the defects, pull that out, though it comes from a single image, and now we have 5 different images coming out from one specific image, for that matter. And now this becomes 5 different images, and each one is now classified through that algorithm that we have, this 4-class cluster, to say which one it belongs to. And for example, this one could be this type of defect that we would have crapped and we would have got this, and then it went on. So different cluster could be talking about different types of defects. Now, at the end of this, what we got is the first crop follows defect type 1, the second crop defect type 4, and so on and so forth. So if there is more than 5, 6, just as a sample example. Okay, in our case, we had only 4, but this can go on and on. Now, you realized that in this process, we have not only identified the area where there is a defect, we have taken it aside and also classified as which type of a defect it belongs to. Okay, good. So at the end, we say that this particular sheet or this particular image or part has multiple defects, and those defects are defect type 1, 4, and 5. This is the kind of analysis we can give. But if we also want to know, then the next thing is what's the magnitude of that image. Okay. Before going to that, one other challenge that we faced was that when this is the image and this is the cropped part, now what if the part had a hole like this, but that hole is a genuine one? That means to say that's the requirement of that particular product. Okay, and it is not an anomaly. Okay, so we had to make sure that we could identify only the anomaly and not actually pinhole the hole as a anomalous one. Okay, so the way we went ahead and addressed this particular kind of a challenge was we compared the first one with the first cluster, which had the bigger sample size. Any of the image in that good part is a reference image to say this is exactly the part is. So when you compare it with that and remove all the required parts from this, so it could be an amazing design that could be present. It's able to difference that out and remove that piece aside and only identify the defective areas. Okay. By that, we were able to address cases of not confusing with the anomalous versus the non-anomalous or the normal region of any kind of a part that is produced. Okay. And next is to find the area or the magnitude of the defect. The magnitude of the defect, in simple terms, in the process itself, we realized the area of the defect was easily identified in the form of pixels. The area of the pixel or the quantity of the pixel is an indication of the magnitude of the defect. And that pixel is nothing but the contour that was drawn around the defective area. Okay. And accordingly, we went ahead and classified. So we made that into three different categories as small, medium, and large. So anywhere if the area of the pixels, maybe if the pixel ranges from this to this, then it's called as a small. If it's this, medium, and large, and this kind of dependent from part to part, from customer to customer, and how sensitive things are for that matter. Okay, great. So this is, by the end of this, now we have identified the magnitude from the contours as well. Happy to say that we have reached more than 90%. So on a very pessimistic note, if I just take this to a very generic place and start implementing this and integrating without manual intervention, without any need of a customization, we are still able to achieve more than 90% accuracy by the way we have organized the algorithm. So it's kind of taking care of most of the uncertainties that are there in the various types of products, and small details have been also addressed. In this particular example that I've been going through in the sample examples, you can see that we have got up to 93% accuracy in being able to classify the whole narration for that matter. Okay. In summary, I can say that in an unsupervised data science approach, we are able to annotate the different types of defects for any kind of a manufactured part. We have also been able to carve out and say if there are more than one type of a defect, and also give the magnitude. So on a holistic note, we are giving the complete information without any need of interference from the manufacturing domain and a lot of subject matter experts, so which is now making them much more easier to get started solutionizing most of their things, rather than having that, only if you facilitate me 3,000 images all annotated, then we will. So whichever was an hesitation part to work is kind of minimized, and now we are able to take this forward in a much more positive and neat note to our customers. With that, I thank one and all for the very patient listening, and I'll be happy to take any questions that you might have.